Hello everyone, welcome to Analog Circuit Design. This is Lecture 2. We'll talk about basic circuit theory and MOSFET basics. I'm Tae Kang. Before starting, I would like to acknowledge uh, two people. This slide mainly refers to my PhD advisor, Michael Flynn, lecture note, which is ECS 413 and ECS 311 from University of Michigan. Mike is a world-renowned AZ expert. He was he's an amazing advisor. Also, the slide refers to the lecture note of Dr. Seung-Jong Lee. He's also an ADC expert. For example, he got a VLSI Best Paper Award for ADC paper. He's working in Qualcomm, USA. He's a very good friend of mine. And then he also got a PhD from Mike's group from University of Michigan. Our textbook is Design of Analog CMOS Integrity Circuits by Razavi. Here today's lectures outline basic circuit theory, KCL, KVL, Thevenin, and Norton, and then we'll cover some MOSFET basics. Let's start with the basic circuit theory, that is Thevenin equivalent and Norton equivalent. When we look at the circuit, the Thevenin equivalent has one voltage source and one input resistor. And Norton equivalent circuit has one current source and one input resistor, which is in parallel. So the important point here is that Thevenin equivalent must have a single voltage source and single resistor. If there is multiple voltage source or multiple resistor, that's not Thevenin equivalent. This is the same for Norton equivalent. There must be a single current source and a single resistor. So what is it then? The beauty of these circuits are any linear electrical network. You can just say this is like any circuit, linear circuit, which has only voltage and current sources and resistors. So it doesn't matter how many voltage sources, how many current sources, and how many resistors it has. It doesn't matter. But what it says is no matter how many voltage sources or resistor or current sources that some complicated circuit has, we can always like replace them with either of them, which means we can compress that complicated circuit to either of this very simple circuit, for this with voltage source or current source. So why are they important? As I said, because it makes the circuit analysis very simple and intuitive. As I said, what we do with this is we replace a very complicated circuit with this simple circuit. So since the complicated circuit becomes this simple, we can kind of have an intuition on that. So this is really helpful when we design circuits. So the following slides will cover how we convert circuits, like complicated circuits, to both equivalents. Also, we will learn how do we convert them each other. So they are like we can convert them. They can go back and forth between them, and then we will do some like calculation exercise too. Also, like the proof of this sentence, that any electrical circuit can be replaced. The proof is in Thevenin's original paper. If you go to this Wikipedia, you can check. I think they kind of explain it really well. Let's start with Thevenin model. Here's an example circuit, very simple. I'll stop the lecture and then calculate here on your own. Here's the answer. The total current that flows from this current source I mean, voltage source is Is. Then that's like Ohm's law, Rs plus RL divided by voltage. So Is represented like this. And then the voltage over this resistor it's also like Ohm's law, V equal Ri. We know Is now, and then so we substitute this Is to here, and then the final equation looks like this. Well, actually, this is also a voltage divider, so you don't have to calculate the Is. You can just directly using the ratio of Rs. I mean Rs and RL. And this is the like a side question. Assuming that this is a voltage source, so you want to provide some power to the output load, would you like big RS or small RS? The answer is small. We want small RS input resistor because we want to provide more power to RL, because in the previous slide, the output voltage here is represented as the voltage divider. So if RS is small, that means more voltage goes on here, so we can deliver more power to RL. So like for example, there's a power supply or some voltage source. We want to make the input resistor, series resistor, as small to provide more power to the load. Now Norton equivalent. Please stop the lecture and calculate the current I/O on your own. To calculate it, we can use KCL. So assuming that this node voltage is Vs, and KCL means that at the single like node, the sum of the current outward and inward must be 0. So for example, because Is is coming to this way, so Is is coming to this way. When we look at this area, because current is coming in, then we have to get a same amount of current out. So Is, which is inflow current, equal to the current through here, which is Vs divided by Rs, and also the current to this way, which is Vs over RL. So this is using KCL. And then if we like do some little bit of math, calculation, then it turns out to like this. So this is like a little tip. Whenever I calculate, I always check the order. So since V is Ri, voltage is resistance times by current. So when you see the order, it's fine, right? So current, and there's two resistor divided by resistor. So the order of this part is resistor. So current times resistor voltage. So I think it's a good habit, good things to check this order. So if we substitute this Is to here, we got, so IO is like Vs divided by RL, and then we can substitute Vs from here, and then we got this. Well, this is actually a current divider. Similar to Thevenin equivalence, what is better for Norton equivalence? I mean RS. So assuming that this section, I mean just this part, is let's say we have a current source. Every current source has its input resistor. I mean input resistance. Well, impedance, but the same here. We'll only talk about like real parts, so which is resistance. So assuming that this is our like current source, we want to deliver current to certain load. So what's better? Here we would like to have large RS. This is opposite to Thevenin. In Thevenin, in voltage source, we said we want small input resistance. But in Norton equivalent, we want large resistance. because if this RS is large, most of the currents will go through the load, which is what we want. So we want to deliver more power to the output. So we want our input resistor in current source as large as possible. So far, we talked about Thevenin and Norton, the basics. One thing that's really important is that every linear electrical circuit can be replaced by either Thevenin or Norton sources. And then again, the important thing here is that Thevenin source must have a single voltage source and single resistor. And then Norton source must have one single current source and then parallel input resistor. And then we also do some basic calculation. And here's the question. As I said, every circuit can be represented in either Thevenin and Norton. I mean, they can, those two always exist. I mean, we can represent it with both. So it means that we can switch between them. One, like for example, if there is a complicated electric circuit, and then let's say we replace those complicated electric circuit with this Thevenin equivalent. What we can do is we can convert that Thevenin equivalent representation to Norton circuit representation. So they can be converted back and forth between them. First question, why? Why do we need to switch them? Can we just use Thevenin all the time, or can we just use Norton equivalent all the time? Can we just use whatever you like, whatever I like? No, it's not. Each of them has their own like purpose. In some situation, we need Thevenin. In some situation, in other situation, we need Norton. And the next question would be, how do we switch them between? How do we switch between them? Let's start with some simple example. Here is a Norton equivalent circuit. Can we make it as Thevenin equivalent? This can be a little tricky if you haven't done this before, so let's do it together. What we have to do is we need to calculate this is Norton. If you want to get a Thevenin equivalent, this is how it looks like, right? There is a 1 voltage source and there is one resistor. What we have to do is we need to find this VTH first. To find VTH, open circuit, make an open circuit. So here, this is already open circuit. And measure voltage here. So what's the voltage here? Because if this is open, the current fully flows to here, right? So the voltage, the open circuit voltage, VOC, would be this, IS times RS. So that's a Thevenin voltage. And let's find RTH, R Thevenin. So this part is a little tricky. What we have to do is we need to zero all the independent sources. So for example, the voltage source should be short and current source should be open. What do we have here? We have current source, right? So what we have to do is we have to open it. Open it means just remove it, and then these are not connected. Okay, so current source is open. That's done. And then measure the current. Measure the resistance in this term. So it's like measure this resistor, R in. R in would be what? Just RS, right? So RTH would be same as RS. So those rules apply for every complicated circuit. When we measure, when we get a like Thevenin voltage for any complicated circuit, first thing we have to do is open circuit open circuit the output terminal, and then measure VOC, which is open circuit voltage, and then that VOC will go to this VTH, Thevenin. And to find this RTH, zero out all independent sources. Voltage source will be short, and then current source will be open, and determine the equivalent resistance, RTH. We'll do a lot of exercise for this, even after, next week. So don't worry. Here's another example. Can you guys stop the lecture and then try to do some hand calculation here and then get a Thevenin equivalent of this circuit? To convert the circuit to Thevenin equivalent, first what we have to do is we need to get a VTH. The way to do it is, so here's the output node. Measure the open circuit voltage. So this is already open circuit, right? And if we calculate the voltage here, this is a voltage divider, so it can be easily shown as a VOC, which means open circuit, is actually the VTH that we want to get. And so it will be a voltage divider between resistor. So V1 times R1 plus R2, and then R2. So this value will go here. And then next, we have to calculate this RTH. To find RTH, zero out voltage source, because we have voltage source. Short. So if we short this, and measure output resistance. So if you measure output resistance here, you see that these are like parallel connection. So these are parallel resistor. So RO would be, which is output resistor. The input, well, actually, that's input resistor. But anyway, so RO, that the measured R here is RTH. That's RTH I want to get. And that's the R1 parallel R2. These are how we represent a parallel connection. And then that would be like this. So this value will go here. Now this is time for Norton equivalent. Kind of similar to Thevenin, but a little different. Like, for example, to find INT, we have to short circuit the output. So, because it's simple, when you think about this, if we short this, what current will flow here? Because if we short this, because it has a resistor, all the current goes to the short one. So that's why. If we short it, then the current will go here. So that's how we measure the INT. And then to find Rn, zero all the input, like independent sources, the same. But in Thevenin, there was voltage source, so we shorted it. But in Norton equivalent, we have only a single current source, right? So to zero out this, we have to just open it. So open it means just remove it, and then measure the resistors here. Here's how we calculate it. So our purpose is there is a certain circuit, and we want to convert it to Norton equivalent. So again, the Norton equivalent has a single current source here and then single resistor. To find current TN, current Norton, what we said is measure short circuit current. So if we short here, then current will flow to this way. So the current will be V1 over R1. So this number will go here. And now what? To find R Norton, zero out voltage source. So this voltage show will be short, and then measure the resistance. So this is the same case for the previous Thevenin conversion. So R out would be RTH, RNT, and then that's the parallel of R1 and R2. So now let's move on to MOSFET. So first, why MOSFET? Why do we use MOSFET? So this content is from Rajavi book. First of all, MOSFET stand for metal oxide silicon field effect transistors. Who invented it? J.E. Linenfeld in early 1930s. Well, I'm not sure how to pronounce Linenfeld, but anyway. Um, and then MOSFET. So this is an interesting point that the MOSFET is invented way before bipolar transistor. So this is interesting because people use bipolar transistor first, but it turns out MOSFET is invented first. So, but why people couldn't use MOSFET at the very beginning? Because there was a fabrication limitations. So, which means the fabrication limitation means that people cannot make MOSFET small enough. So, if MOSFET is not small enough, it's like performance is not good. So people use bipolar transistor first until the most until the MOSFET became practical, and then it became practical only after early 1960s. At this time, they use only N-type, but in mid 1960s, finally CMOS, complementary MOS, is invented. So So, I mean, we will cover why they use C. Well, basically, they use complementary because there's P and N type, so they're kind of opposite. Um, so the advantage of CMOS over bipolar transistors is it only consumes power during switching, which means it has low like steady current consumption, steady power consumption. We'll figure it out. We'll cover it more like in our whole later lectures. And then the Razavi book says it requires fewer devices to design certain function, certain block. Well, I'm not get this part clearly, but this is not our like um, part to cover. So, but this is important. The advantage of CMOS over bipolar is CMOS can scale. I mean, scaling means CMOS can become smaller. I mean, that's one of the like biggest advantage. So so we can scale CMOS well, which means it allows CMOS faster operation. And then the last thing is low operating supply voltage. Um, this is good because it allows us to save power. So now let's see more detail. I mean, what is MOSFET? Anyway, so we get that MOSFET is popular, but what is MOSFET? Again, metal oxide semiconductor, field effect transistor. And this is how it looks like. There's gate, source, drain. This figure is from Razavi. Basically what it does is a switch, a switch from source to drain. So, so from source to drain, the current is flowing. And then we can control the current flow from source to drain, or maybe drain to source, doesn't matter, by controlling gate voltage. So, so just understand it as like a switch. So, okay, we get that. This is how it looks like, but how can we design, how can we use this MOSFET to analog circuit design? So in the previous slide, we talked, as I told you, that the gate voltage controls the current flow between source and drain, which means the gate voltage controls the resistance between source and drain. So that's why it's kind of a the resistor has transition. So it's like trans resistor, changing resistor, transistor. That's how they got named transistor. And how does resistance vary with VG? That's the important point, right? So we'll cover that later. I mean, in the following slides. So and then what about drain and source voltage? I mean, we told them that the the voltage of the gate changes the resistance. Then, but like, how about does the voltage of source and drain Im impact on the resistance between them, or how fast can we go? I mean, how fast can we change? How fast can we trans resistor? Well, this is actually related to the capacitance, which is related to the area. I mean the size of this transistor. So, I mean, just keep in mind that we are using this three. We'll see a lot of this transistor, this MOSFET, in later. Um, and then the main purpose is that the gate voltage controls the resistance between source and drain. Now, you may wonder why, how do they named those three ports? Well, gate is kind of intuitive, right? Because it's kind of a controlling the current, so it's gate. But why source and drain? Because because this port is source in NMOS, because this is a source of electrons. This one is collect electrons. So draining, in other words, draining. That's why it's drain. So electron flows from here to here. But the tricky part is the current flow direction is from here to here. They're opposite. You see that here, electron flow direction is opposite to current flow direction. Because when we define the current flow direction, we focus on plus ion movement. But in NMOS, electron is moving. Electron is a carrier of current. So in NMOS, minus ion is moving. So I think this is good to know, and very important. So we talked about the symbol of transistor before. Now, now let's see how actually the MOSFET looks like. So this figure is also a simplified version of transistor, but it's really like this, like similar looking. Um, so basically, you see that there is P substrate overall here. So all of this MOSFET, like gate or drain or source, are fabricated on top of this P-type substrate. And then we call this as bulk or body. Um, we'll come back to bulk and body. This is important. We have to control the voltage of bulk and body well to operate this MOSFET like properly. And then how about source and drain? See, here's source and here's drain. You see that there is N plus, and then like different color. Why? These are like heavily doped N regions. So what they do is they, in on top of this P substrate, they like shoot the ion beam, so make its electrical characteristic different. The next one is gate here. Gate is made from polysilicon, but which is heavily doped, so it becomes conductive. We call it like simply as poly. So here's the gate. And then the other thing is oxide. The oxide is here. You see that? Uh, like a thin layer between gate and P substrate. So this is silicon dioxide, which is SiO2. Um, the other thing is the current actually flows from here to here, like this horizontally. The current flows. So this is the like interesting things happening here, right? Um, and then here's the length and width. So length and width is a parameter, the main parameters for MOSFET design. So these are dimension. L is from here to here, and the width is from here to here. So we can also kind of relate this value to resistance. Like for example, let's look at the length. So length is here to here, right? And then I told you guys that the current is flowing from source to drain through this path. So what happens if length is long? It has to travel a longer distance, which means for current, so current has to travel between from source to drain. But if the length is longer, which means the current has hard time to travel. If current has hard time to travel, which means the resistance is large, right? Because R is equal V over I. If current is large, then resistance is small. So again, if L is large, which means current has hard time to flow, so resistance goes up. And what about width? Width is here. If we have larger width, it means there's a more path for currents to flow, right? Because currents is flowing here to here. If width is large, then currents is from here to and then there also too. So current has easier time to travel between source and drain, which means the resistance is small. Again, if we have larger width, the resistance of this MOSFET becomes smaller. We can talk about a little more detail, like effective length. So effective length is actually this. So when we draw transistor, we draw the actual length. I mean, not an actual length. The physical length is from here to here, but due to the side diffusion means this area. You see that? This area. So because of that, the effective length is like smaller than the actual length. For example, the minimum L effective is 0.13 micrometer in 0.18 micrometer CMOS. So we usually call this CMOS as 180 nanosiemens. So again, in 180 nanosiemens technology, the minimum effective L is 130 nanometer. Because I guess some of you some of you are not familiar with this number. So what does it mean? Like why do they put number in front of CMOS? So if I can talk a little more about this number means that's kind of a smallest like length that we can draw in CMOS. Well, actually, there's a lot of stories that like the meaning of this number becomes kind of changing a lot recently, but it's easier to understand that the number in front of the CMOS, this means how small can we make transistor. So for example, when I was in PhD, the technology that I used was 40 nanometer CMOS, which is not like, I mean smaller than this 180 nano, but 40 nano is not also like a not very advanced technology. For example, Apple M3, they are made in 3 nano CMOS. So if the number in front of the CMOS is smaller, that means advanced technology because it's smaller. But anyway, so 180, this technology is kind of a lot of like low power circuit designer in research area really likes to use it because it's cheap. And then it consumes really low power. But well, this is just a side story. Let's come back to the next item. Conductive poly here separate by oxide from the channel. So that means TOX. So these are like 10 angstroms size, but it's becoming like smaller. Well, and then as I said, this MOSFET is first proposed by Linfield and Hale in 1930. Yeah. Since we saw what MOSFET actually looks like, our next interest would be the design parameters. In MOSFET design, we design the dimensions. Like we're changing the size, the area. That's how we design the MOSFET. Well, we also changed the material of MOSFET. Like for example, like this N plus or maybe this oxide. I think it's mostly about doping change. So anyway, we also changed the material of MOSFET when we designed the circuit. So in like for example the amplifier, we sometimes like mix and match multiple types of MOSFET. Like for example, there's a MOSFET with high VTH or low VTH or very low native VTH, native MOSFET. Uh, don't worry, we'll learn about VTH later. But anyway, um, when we designed it, we also changed the material. But those things may be a little too advanced topic in today's lecture. So now at this moment we'll just focus on like physical dimension design. Well, anyway, long story short, circuit designer changed the size of MOSFET. That is, circuit designer selects width or length. And the interesting point of MOSFET is it has a huge flexibility in selecting dimensions depending on the applications. What it means is the range of size, the area that we choose in a single design varies, has a lot of very wide range. Like I'll say the MOSFET size has a huge dynamic range. Like it means this, for example, if we compare the smallest MOSFET versus and the largest MOSFET in a single chip design, it can easily be over 10,000, 10K, 10,000 times different. So one can be 10,000 times larger than the smallest one, or even more. So that's what it means, huge flexibility. And that happens a lot. Like for example, the length, um, some circuit need like minimum length, but some circuit need larger length. For example, like amplifier. So the minimum, when we say minimum feature, it depends on technology. Like it is technology 180 nanometer, or like was it 180 nanometer, or like 40 nanometer, depends on that. So minimum features are different, but in those technology, we can also use like tens of micrometer length of, well, micrometer length. That's like already 1,000 times, right? We can talk a little more about that dimensioning, like sizing. For example, length. In digital circuit, always use minimum length. But in analog, we don't usually use like minimum length. It's because digital, because I'm also doing digital circuit. Digital should be very fast, and um, it's like very robust to how do I say, like a variation. Um, so I'll say digital is immune to noise, but analog is not. So that's why we kind of need larger L. If length is too small, for example, it's kind of like hard to fabricate, right? It means it tends to have more variation. So we kind of need more stable length. In width, this is also the same. Um, in like we don't really use like minimum width. Well, actually, that's not true. In lots of circuit that I designed, I use some minimum width, but those are like kind of specific purpose. Well, anyway, the width circuit doesn't really use a minimum width. It's kind of larger than that, but also it has a huge difference, as I said before, like length. Like maximum width can be a centimeter size. But this centimeter So centimeter is a huge thing. When we design a chip, like not like a huge like Apple M3, those are huge chips. But maybe when we talk about like research purpose chip, those are usually like in millimeter scale, like 1 by 1 millimeter. Or if the chip is really large, then 2 by 2. For my experience, my research purpose chip was mostly like 1.2 by 1 millimeter size. But again, for company chip, those are a lot larger. Like when I was in Apple, well, maybe I shouldn't say it. So anyway, um, so I'll say the chip size can be like millimeter scale. So what do you mean that the chip has centimeter scale? It doesn't make any sense, right? What it means is that when we actually design the MOSFET, it has multi-finger. So if the width is here, the total width of this MOSFET is 4 width because there's 4 MOSFET. So these centimeter MOSFET is not like actual like a start to end centimeter. It has a lot of fingers. So assuming like if a finger is 100, then each of them width would be what is it? Centimeter, 1 centimeter divided by 100. That's like 10 milli. Okay, 100 micro. So now that makes sense, right? So anyway, when we say centimeter, it means a total width. What I want to say, in long story short, the MOSFET has a huge dimension like range. And this graph shows that the L minimum is keep decreasing through year. It's related to Moore's law. Um, so that's kind of an advantage of MOSFET. We always try to scale the dimension. I mean the length. Like for example, I said it before. Like Apple M3 used 3 nanometer technology, and then people are working on 2 nanometer, um, like for example in TSMC or something. So far, we have ignored the substrate on here on which the device is fabricated. Hence, the symbol was 3 ports. But in reality, the substrate potential, P substrate for NMOS, greatly influences the device characteristic. So the MOSFET is actually a 4-terminal device, and we call it as B, body or bulk. For a typical MOS operation, the PN junction here, PN here, must be reverse biased. It means the P substrate should have lower potential than N plus region. So we connect this P substrate to the most negative supply in the system. That's usually 0 voltage. The actual connection is usually provided through this P plus ohmic region. Now let's look at the PMOS. PMOS is similar to NMOS, but you see the difference. NMOS has NMOS source and drain is N plus, but in PMOS they're P plus. They're kind of opposite. And it's fabricated on N substrate. While in NMOS was fabricated in P substrate. So they're like you can think of it as opposite. So this is the same with NMOS. Potential of N substrate influences PMOS characteristics a lot. Same. So connecting substrate to the most positive potential, usually VDD supply voltage, because we need to same. We need to make a reverse bias between P and junction, P and N junction. So because P is here, if we want to make a reverse bias, we have to make N side potential higher than P side. So the PMOS symbol is actually like this. There is one extra port, which is bulk and substrate. But here comes some interesting thing happens. So in CMOS technology, which is complementary MOS, because it's complementary because you see that NMOS and PMOS are just complementary set. They are opposite. So in CMOS, both NMOS and PMOS transistor are available. We have to use both of them. But NMOS and PMOS they have different substrate, but they have to be fabricated on the same wafer. Same wafer means same substrate. So wafer substrate is P substrate. So again, NMOS, it has P substrate. Oh, it's good. But PMOS, it needs N substrate. So what people do is they put N well here. So it's kind of isolating its substrate, N substrate, from like the global P substrate. You can just think of it as like a wall here. I mean, they dope this P substrate with anion again. So similarly, we connect this bulk, which is here now, because it's N-well. We need, if we want to give a potential to N-well, we have to use this N plus, like ohmic connection, N plus region. So we connect this B to, as said in the previous slide, to the most, like the highest potential, which is usually VDD. We learned that the MOSFET has 4 ports. And here, let's wrap up the MOS symbols. There are like 3 types of symbol that we draw. First, analog. So you can see there's 4 terminals. The 4th terminal is bulk. And in NMOS, the bulk corresponds to substrate, P substrate, and PMOS bulk corresponds to N-well. And you see that in NMOS, drain is on top, and PMOS is source is on top. This is because usually when you draw a circuit, it's better to put like higher voltage node on the top. So it means that if you go from top to bottom, the voltage usually goes down. So in NMOS, not usually, but most of the time, drain has higher voltage than source. In PMOS, source has higher voltage than drain. And you may wonder why are they different? In NMOS, source, the carrier. So the carrier in NMOS is electron. So, and then the source means the source of carrier. So in NMOS, the carrier is electron, and so the electron flows from source to drain. Again, in NMOS, electron flows from source to drain. So in this direction. But as I said before, the current, when we define the direction of current, we focus the positive carrier is like the reference. So electron even electron flows from source to drain, the polarity of electron is minus. When we say the direction of current, it's opposite. So the current flows from D to S. Maybe a little confusing, but again, in NMOS, source means the source of electron, because electron is a carrier in NMOS. So in NMOS, electron flows from source to drain. But when we define the direction of current, the positive polarity is a reference, so the current flows the opposite direction of electron. So current flows from drain to source. And since current flows from higher voltage to lower voltage, and I said current flows from drain to source in NMOS. So drain has higher voltage. So current flows here. So here, current flows here. This is current I. Let's look at the PMOS. In PMOS, the carrier is holes, and the polarity of hole is positive. So again, hole flows from source to drain, so in this direction, and then the polarity of hole is positive in this case. So the current flows from here. So in both cases, the direction of current is the same from top to bottom, and then current flows from higher potential to lower potential. In PMOS, source voltage is higher than drain. In NMOS, drain voltage is higher than source. And then let's move on to the next symbol. This is also used for analog circuit drawing. The difference between here and here is that in this case, they don't have a bulk notation representation. They just omit the bulk connection here because it's simple. It's easier to draw and it's neat. The assumption here is that when the bulk of NMOS connects to VSS, which is the lowest voltage in circuit. In PMOS, since there's no bulk connection, the assumption is that the bulk is connected to the highest supply in the circuit, which is VDD. In this textbook, I think most of the case they draw like using this rather than bulk, because like majority of the MOSFET in analog circuit, their bulk is connected to either VSS or VDD. But not always. There's a case that we don't connect them to those. We will cover that later in like later lectures. But anyway, keep in mind that even though they do look like a different, but they're the same thing. How about digital? In digital, you see that there's no arrow, right? So in here, you see the arrow is in source side. In NMOS, arrow is here, and then PMOS arrow is here. And then the direction of arrow, it goes to here because it represents the direction of current flow. So current is flowing from here, the drain to source. But in NMOS, they don't have any arrow because in digital circuit, MOSFET is simply operate as a switch. So sometimes in digital, it's like 50 to 50%. Sometimes the current flows from top to bottom, but sometimes current flows from the opposite side. So that's why in digital, they don't kind of differentiate source and drain. Now let's dig in more NMOS operation. Like how does it work actually? So assuming the circuit voltage situation, you see that this is NMOS, and N plus this is source. Source is connected to ground, and then we apply some VG on the gate, and the drain voltage is 0.1 volt. So it's if we represent it in schematic, it looks like this. The source is connected to the ground, and drain is connected to 0.1 volt, and there's gate voltage. And then we start to increase VG. When VG reaches a certain voltage, holes in the P substrate, this area, are repelled from the gate area. So holes, the polarity of holes are positive. So since holes are repelled in this area, the sign is negative. There are negative ions left. And we also call this as depletion region, but there's no current yet due to no charge carriers. So these are not charge carriers. It's just since the holes are repelled, the negative ions are just left, and they are not carriers. Okay, here, but let's keep increase Vg. So finally, if we increase Vg enough, the electrons here flow from drain to source. And we call this group of electrons as channel. So this electron is actually moving from here to here. To electron moves to here. No, actually it moves to here. So the current, since the current flow is from here to here, right? Because the current is opposite of electron, the polarity direction. So here the point is, if we keep increase the Vg, the electron channel forms, and then finally current flow. This channel is also called as the inversion layer because of the polarity is minus here. And the Vg that form the electron channel, that's what we call it as a threshold voltage. So long story short, if the Vg is higher than threshold voltage, then current starts to flow because the channel is formed. That's why we call it as threshold voltage. Once we over this voltage, which means threshold, the current starts to flow. And this slide shows how do we calculate the threshold voltage. I just brought some paragraph from the textbook. This is kind of complicated. I suggest you read it, but it's okay if you don't understand it fully. This is fine. This is more like a device area. But maybe the one thing that it's good to remember is this number. We'll use this number for later, like a current calculation. So rather than that, if you're interested in, read this, and then maybe you can find some more thing on the website. But in this class, that's fine. But this part will be kind of interesting. So this is also from the textbook. What it says is, without any special process, the VTH works around zero voltage. It means that it's hard to turn off the MOSFET. This is actually important thing. So we call this as a native VTH. So there is a device type in actual, when we design the circuit, there are multiple types of NMOS. And one type of NMOS is native NMOS, native MOSFET. That means they don't have any VTH. I mean, their VTH is zero, which means that they're always turned on. We use it sometimes. I also have used that for some specific, some certain purpose. But overall, usually that's not good. We need some controllability on turning on and off the MOSFET. So they kind of implant some P plus dopants, like in here, this P substrate, I mean this area, to change the threshold. It's more like to increase the threshold. This is the end of the lecture today. We'll cover more detail on like the current equation about MOSFET and then look for more circuit things. Thanks for listening.